guys, what I want to do now is I want to finish up section 7.5, and I want to talk about independent events. Now, the definition of independent events is fairly intuitive, okay? We'll actually come to a formula with this. Again, as always, you do not have to memorize any formula. Formulas will always be given to you. You just need to know how and when to use it, okay? So, let me start out by saying the following. Two events are independent if the outcome of one event has no influence on the outcome of the other event. Will you guys grant me that that's kind of an intuitive thing? Okay? Now, this is different than mutually exclusive. Remember, mutually exclusive events can't happen at the same time. All we're saying here is that they're independent if the one of them or both has no influence on the outcome of the other. Okay? Now, what I'm going to do is I'm going to make another comment here, which is going to help guide us to the formula that we're going to be using for independence. So, if events E and F are independent, will you guys grant me then knowing E has occurred gives us no information on the probability of F. Okay, does that make sense to you guys? If these guys are independent, then just because one event happened, whatever came of it, it doesn't affect anything with the other event. So, for example, if we're assuming E and F are independent, then knowing E has occurred, will you guys grant me that has no bearing on the probability of F? Now, using the notation for the conditional probability, doesn't that mean that the probability of F, given that E happened, is just the probability of F? Or similarly, the probability of E, given that F happened, is simply equal to the probability of E. Okay? This is using the notation for conditional probability. And I'm only showing this to you guys right now because I'm about to get to a formula where I need to use this. Okay? Again, this says, hey, we want to find the probability of F given that E happened. But if these guys are independent, E is totally irrelevant. Therefore, it's just the probability of F. Similarly, this is the probability of E given that F happened. But again, if these guys are independent, who cares if F happened? It's just straight up the probability of E. You guys with me this far? All right then. So, what we then want to do is say, well, if we went back and drew a tree, don't have to write this down. Wasn't this guy the probability of E? Isn't that what that branch was? And wasn't this branch that was given to us the probability of F given that E happened? Right? It was given to us as a conditional probability. What happened when I wanted to find the probability of the branch of a tree? what did I do to those two probabilities? I multiplied, didn't I? Didn't we say, oh, the probability that E and F happens, isn't that equal to the probability of E times the probability of F, given that E happened? We just multiplied along the branch. But if these guys are independent, what is the probability of F, given that E happened? Isn't it just the probability of F? So I claim, if you haven't written anything down yet, now is when you want to start writing. The way you test the independence is as follows. Two events, E and F, are independent if the probability of the intersection is the product of the probabilities. Isn't that cute how it came from our trees? I think so as well. Okay. Do not try to use your intuition with these if I ask you whether two events are independent, because I can finagle the numbers to come out that even though intuitively you would say that they are independent, they might not be, or vice versa. Okay? So, the way you check independence is as follows. Alrighty, so let me do a couple of examples. Suppose I tell you events A and B are independent. And I know that the probability of A is 0.25, and I know that the probability is 0.2. What I want to do is find a couple probabilities. I want to find the probability of A intersect B, and then I want to find the probability of A union B. Now, if this is funky at first, don't worry. This is why you come to class. Okay? Are you guys ready? Cool. All right. You're given that events A and B are independent. You guys, a total knee-jerk reaction when I tell you two events are independent, in the back of your head you're thinking, oh, that means the probability of the intersection is the product of the probabilities. We know that because we're told that they're independent. Okay? You guys see how I got that? Alrighty. Well, anyway, what's the first thing we wanted to find? Oh, cool. I want to find the probability of A intersect B. Do I have enough information to do that? I totally do. Because I know these events are independent, I know that the probability of A intersect B is the probability of A times the probability of B. What's the probability of A? 0.25. What's the probability of B? 0.2. How's that? Isn't that sweet? You guys with me? All right. So we got 0.05 here. Can I get the probability of the union now? I can. Think back, you guys. Do I have a rule that tells me how to find this probability? I absolutely do. What's it called? The union rule. You're not allowed to forget anything, you guys. Except the formulas. But you have to know when to use them. Isn't the probability of A union B equal to the probability of A plus the probability of B minus the probability of the intersection? Now, maybe you wouldn't have thought of using that, but again, that's why we took the class. Okay? So, what's the probability of A? 0.25. What's the probability of B? 0.2. Oh, do we know the probability of the intersection? We sure do. We just computed it. So we get 0.4. Was that fun? Great. Do you want to do another example? Great. Me too. So, suppose now I'm asking you, are events A and B independent? And I'm going to tell you that the probability of A in this example is 0.5. The probability of B is 0.7. Okay, and let me give you one more thing. And suppose I tell you that the probability of A union B is 0.85. Sorry about that. Now you can read it better. Okay. What is it that we're wanting to know? Are they independent? Well, the way to check independence is you ask, is the probability of the intersection equal to the product of the probabilities? You all agree that this is what we're looking for here. Okay. Well, do we know what the probability of A is? We sure do. It's 0.5. Do we know what the probability of B is? It's 0.7. Do I know the probability of the intersection? No, we're not given that yet, are we? No. What am I given? The union. But you guys, if I've got the union and I've got the probability of A and I got the probability of B, can I get the probability of the intersection? Totally. Let's do this. Probability of A union B, probability of A plus the probability of B minus the probability of the intersection. What was my union? 0.85. What's the probability of A? 0.5. What's the probability of B? 0.7. And this is what we're looking for. Now, I am going to show you every last step of doing this, just so I'm sure that you guys are okay with the algebra. Okay? If you can do this on your own already, ignore me for a bit. 0.85 is what we have on our left. On my right, what is 0.5 plus 0.7? 1.2 minus the probability of A intersect B. Guys, with me this far? Yeah? Okay. Now, when you're doing some algebra and you want to solve for your unknown, don't you want to get him all by his lonesome on one side of the equation? Yeah, you want to isolate him. So don't we want to move this 1.2 over? How would you move a positive 1.2 over? You would subtract it from both sides, right? Equations are like kids. Whatever you do to one side, you got to do to the other side. Okay? Well, on my left-hand side, I have 0.85 minus 1.2. What do I get there? Negative point what? 35. Put it in your calculator. Don't want to do it by hand. And isn't that negative the probability of A intersect B? See, I scooted my 1.2 over, but I still have a negative sign in front of there. But if I have a negative on both sides, can't I say, oh, multiply through by -1, so the probability of A intersect B is 0.35? Are we done with the problem yet? No, we only now have enough information to answer it. Remember, I wanted to know, are these guys independent? Did we find the probability of A intersect B? We did. We got that to be 0.35. Is that equal to 0.5 times 0.7? Yes! And therefore they're independent. Wasn't that fun? Yes. Okay. Why did we have to go through this whole rigmarole? Because we weren't directly given what the probability of the intersection was. If I'm asking you independence, you always want to find the probability of the intersection. Now, wouldn't the problem have been a lot nicer if I said, hey, are A and B independent? And I told you that the probability of A is 0.4, the probability of B is 0.7, and then I told you that the probability of A intersect B was 0.35. Wouldn't this one be a lot simpler to determine? The reason why it would be a lot simpler to determine is everything was handed to us. The only thing then that we would have to verify is we'd have to say, hey, is the probability of A intersects B equal to the probability of A times the probability of B? Well, let's answer this very interesting question. What is the probability of A intersects B? 0.35. And we want to know, is that equal to 0.4 times 0.7? And what are you going to say to me? No way! So they're not independent. Thanks. It's the last minute one. All right. Let's answer one more independence question using a table. Let's have event A and A complement and then total. And then we have B, B complement, total. And I don't know, let's fill in numbers. How about a 4? What should we put in here? 7. Oh my gosh, so that's 11. How about 17 here? So that's a 21. What number should we put in here? 13. Okay, so we have 20 here, 30 here. So we have a total of 41. And all I'm going to ask here is the following. Are events A and B independent? Yeah?
For the last one, would it work every time if we just multiplied, like used the numbers given to figure out like the intersect and plugged in the equation, and if it didn't work?
That would be fine too. Absolutely. That's a lovely question. All right. Well, how do we determine if events A and B are independent? Well, we want to ask ourselves, well, is the probability of the intersection equal to the probability of the first times the probability of the second? You all agree with me this far? Okay. Now, this kind of involves, again, reading tables, but we're pretty good at that. Okay? I want to find the probability of A intersect B. In other words, I'm interested when A and B happen? In how many ways does that happen? 4 out of the total 41. So do you guys agree that the probability of A intersects B is 4 over 41? All right. Now, let's find what the probability of A is. Well, in how many total ways can A happen? 11 out of my total 41. And in how many total ways can event B happen? Isn't that 21 out of my 41? Okay, so 4 divided by 41, we're going to get about 0.09756, and it keeps on going. And then to compute this side, literally, you guys, you could just say it's 11 times 21, and then divide that by 41 squared. Point is, you're going to get about 0.137, etc. Do we have equality here? No! Therefore, are these guys independent? No! Since they're not equal, they're not independent. Yes? But when you multiply two fractions, you multiply your numerators and you multiply your denominators. Yeah. Or you could do 11 divided by 41, get whatever decimal it is. 21 divided by 41, get whatever decimal that is, and multiply them. It's not going to be equal to this side. Alrighty, so one last reminder with the independence and all of this stuff is, you guys, and means intersection. In other words, we want both to happen. You agree? If I have and or, isn't that my union? Right? If A and or B happens, that's by definition my union, right? Because by definition, the union of A and B is A or B or both. All right, so that finishes up section 7.5. What I want to do right now then is I want to start getting into section 7.6. And I think that the best way to motivate section 7.6 is to draw a tree, and what we're going to do is continue playing. Okay? 7.6 discusses Bayes' theorem. Now, Bayes' theorem comes with a really nice, complicated-looking formula. We don't use the formula because we don't need to use the formula. Okay? So, what I wanted to say here is the following. On your last test, you guys had a tree diagram problem, okay? And the tree diagram was given, and you guys got to answer 3 very, very interesting questions regarding your tree, okay? On this next test, you're going to have to do a tree diagram, but you guys actually get to be the ones to fill it out. And not only that, but you're going to have 3 questions, but now you're going to have more questions, okay? You guys may or may not remember we had a really, really nice conditional probability question that came from our tree that we all kind of jumped for joy about because all you'd have to do is read it off your tree. Bayes' theorem gives an additional type of conditional probability question. So what I'm going to do is I'm going to take us through an example or 2 today, and then I'll continue this on Wednesday. Also on Wednesday, we'll be doing section 8.1, but let me tell you the beauty of that section is there's really no new information. It's just, I'm going to keep on talking about probabilities and just writing certain things. So that's kind of a nice relief, I think. Anyhow, let's pretend we have scenario. I think we did one about applicants being qualified and approved. Didn't we do something like that? So I'm just going to do something similar. So suppose for a particular job, 94% of the applicants are qualified. And implicit in that statement, I will say the rest are not. Of the qualified applicants, 89% are approved by human resources. I just write that as HR. Of the unqualified applicants, I don't know, what do you think, 17% are approved? I don't even know why they'd look at unqualified applicants, but I'm also not an HR person. Okay, the first thing we're going to do is draw a tree. Will you guys grant me when I draw this tree that my first branch is going to be whether or not these applicants were qualified? The reason why is because whether or not they were approved was conditional as to whether or not they were qualified. Okay? So, my first branch is going to be qualified or not qualified. And then it will be approved versus not approved. Okay, so what is the probability that a randomly selected applicant was qualified? 94% of them, right? So isn't that 0.94? Therefore, what percentage are unqualified? 6%, we would write that as 0.06. I did this intentionally so that you don't write 0.6 here. Okay? Of the qualified guys, what percentage are approved? 89%, so I have 0.89 here. Therefore, what goes right here? 0.11. These guys have to add up to 1, don't they? All right, of the unqualified applicants, what is the percentage that was approved? 17%. Therefore, what percentage were not approved? 83%. Are you guys okay with me on the tree? Awesome. Okay, so what we're going to do is we're going to find 5 probabilities now. Find the probability a randomly selected applicant now a bunch of these you guys should be reviewed, okay? So, how about part A? Let's find the probability that a randomly selected applicant was qualified and approved. Okay, is this something we can do? Absolutely. Aren't I interested in finding the probability that they're qualified and approved? How do you find the probability of a branch of a tree? You multiply along that branch. So we have what? 0.94 times 0.89. Does this look somewhat familiar to you guys regarding your last test? Hopefully. All right, and if anybody cares, it's 0.8366. All right. What if now I want to find the probability that a randomly selected applicant was approved? Can we do this guy? We sure can. But you look at it and you're like, well, wait a minute. We got a couple possibilities going, right? Approved is here and here. Couldn't they be qualified and approved or unqualified and approved? So they could be qualified and approved or unqualified and approved. Okay? We can certainly find this probability. It's 0.94 times 0.89. What operation does OR tell me? Plus. How about unqualified and approved? What do I write for there? 0.06 times 0.17. Okay, hopefully this stuff looks familiar. We're about to get to new stuff, so hold on. And in case you care, it's 0.8468. Okay, let's do this next guy. Now let's find the probability a randomly selected applicant was not approved if they were not qualified. Okay, what's the magic word here? If. Okay? Now, if tells us conditional probability. Okay? And what I'm going to tell you guys now is the following. When you see the word if, you're either inside going to jump for joy because it's just reading the tree, or you're going to have to do Bayes' theorem. Okay? Let's see what we're going to have to do and how we can tell. Well, what do we reduce our sample space down to in this particular case? All those folks who were not qualified. Aren't we assuming we're right here? Oh, this is a total jump for joy scenario, right? Right? If they're not qualified, in other words, if we're right here, what's the probability that they were not approved? 0.83. Okay? So, I will summarize that something here. Okay? If you're assuming the inner, like this is inner and this is outer, okay? Do you guys agree like this is inside my tree and this is kind of on the outside of my tree? So if you're assuming the inner and want to find the probability of the outer, it literally, guys, is just a straight up conditional. Put a big smile on your face. Read your tree. Okay? This was all last test material. So, let me now ask you this question and let's contrast that. Now, what if I want you to find the probability a randomly selected applicant was qualified if they were approved? I'm going to bring my tree back down. and we want to find the probability in this example that they were qualified. So do you see how this is different than what we just did? Because now, aren't we assuming the outer branch, and we want to find the probability of an inner branch? Okay? So, this is our first Bayes theorem. You guys, we reduce our sample space down to all those folks who were approved. Do you guys agree they could be qualified and approved? Or they could be unqualified and approved. You guys with me there? We reduce our sample space down to all those folks who were approved. Let me show you something. Look up. Didn't we already find that? Yeah. Now, we've reduced our sample space down to these two branches. This is all we're considering. Okay? One of the branches from your denominator is going to be the one up in your numerator, and it just depends upon what you're interested in. In this case, were we interested in the qualified and approved or the unqualified and approved? The qualified. So you would put the 0.94 times 0.89. If this is funky, don't worry about it. We got lots more examples. This is part of the point of coming to class. Okay? Now, just two very quick comments to make. I would suggest you first compute your denominator and then take your numerator divided by your denominator. If you want to put this in as one long string in your calculator, that's fine, but put parentheses around your denominator. You have a smart calculator. Your calculator knows his or her order of operations. All right? And if you just enter this as it stands, 0.94 times 0.89, divided by 0.94 times 0.89 plus this, it would divide before it would add, and you get a probability greater than 1. There's problems there. Okay? So, here is my moral of the story, and then we're going to do one more example. If we are assuming the outer branch and want to find the probability of the inner branch, that, you guys, is Bayes' theorem. We will do one more example on this guy and then continue this on Wednesday. So one more example is, let's find the probability a randomly selected applicant was not qualified if they were not approved. Okay, we see the word if, so we know this is either a straight up conditional question or this is a Bayes theorem question. The way we know is what we're assuming. Okay? In this case, don't we reduce our sample space down to those folks who are not approved? You all with me there? All right. Do you guys agree? In this case, we're reducing our sample space down to these guys. And in this particular instance, we're interested in them not being qualified. If we're assuming an outer branch and we want to find the probability of an inner branch, that's Bayes' theorem. Okay? So, let's do this. In our denominator, we have to reduce our sample space down to all scenarios where the folks are not approved. Do you agree they could be qualified and not approved? Which is a total bummer. Or they could be unqualified and not approved. Do you guys see how I got my denominator here? Okay, once you have your denominator, notice we've got two terms in our denominator. One of these guys is going to be in my numerator, and it just depends upon what we're being asked. In this case, we're interested in them being unqualified. So do you agree that my second term is in my numerator? And in case anybody really cares, I'll compute this just so that you're sure that you know how to compute this. Because I'll tell you, on a test, you guys, you're going to have to compute this. Hold on. And you're going to get about what? 0.325? Anyone else concur?
Yeah.
Cool. All right. I am going to do a couple more examples of 7.6 on Wednesday. Don't worry, I will contrast straight up conditional versus base theorem. Your quiz on